Assalamu alaikum dear students. Today our topic is spherical mirrors. This is going to be a little long one. So first we will start with what exactly are spherical mirrors. So first see this image. Here we have taken a sphere. Don't take it as a circle, it is a sphere. If we cut out a small portion from it, what would we get? We would get a curved plane. A sphere which is hollow from inside when cut down in a small part gives out a small curved plane. Okay, so this plane is called the spherical mirror. Okay, now you know. So basically, when we've taken a really big area just to clarify the diagram. From this surface, when we cut out this type of curve, such that this surface is the reflecting surface of the sphere, then this part of the mirror will be said to have a convex reflecting surface. Okay, why is it convex? Because it just diverges every ray which falls on it. Okay, if a ray falls on this point, it would direct it from away from the center. So none of the rays actually meet at any point each other. Say if one ray falls on this surface, it would be directed to another direction. If some ray falls on this, it would be directed towards this direction. So basically, in convex mirror, no rays meet one another. So they just diverge outwards from the reflecting area. So if the reflecting surface is bulged outward, then this mirror is called the convex mirror. Similarly, if the reflecting surface of the mirror, here we have taken a mirror whose inside surface has the ability to reflect rays of light. Such mirror is called the concave mirror. Okay, now there are some terms or terminologies that we need to introduce in spherical mirror calculations. First is the center of curvature. This is not the center of this mirror. Remember, when you will draw a mirror, you will only draw this part. I have drawn this full circle just to clarify the concept, okay? So that this part was taken out from the sphere. Okay, center of curvature. Center of curvature is the central point of the sphere from which this part was taken. So if we take this sphere, whatever lies in the center of this sphere, suppose we have a ball, so the center of sphere will be inside the ball, just at the center of that ball. So in this case, when we have a spherical mirror, the point inside the spherical mirror which lies at the center of the mirror is called the center of curvature. Okay, next is pole. Pole is the central point of the mirror, not the whole sphere, but of the mirror. So in this case, the central point is this, which we denote as P, is called the pole. Now coming to the radius, if we take this as a center and point P as a pole which lies on the surface of the sphere, then what will be this length called? This will be called as radius. Simple as that. The distance from center to the pole is called the radius. Coming to the principal axis. Principal axis is the line drawn from the pole to the center and extended further. Okay, so if we just draw a line which cuts the this center and extends further, then this line will be called principal axis. This is the axis which determines the radius at any point. If we draw a line here from here to the center, it will be the radius. If we draw a line from this point to the center, it will be the radius. But when we draw a line from the pole to the center of curvature and extend it further, then only this whole line will be called as principal axis. So these four things are really necessary for you to understand in order to do the calculation for spherical mirrors. Now coming to the point, focal length and focal point of concave mirror. Now this time I haven't drawn the whole sphere. I have just drawn the part which we need, the cutout part. Okay, and which mirror is it? This is a concave mirror. You can see it just forms a shape like that of a cave. Okay, that is why it's called concave mirror. Okay, and it's the reflecting surface is inside this concaved part. This is why it's called concave mirror. Now coming to the point. If we take an incident ray, remember in practice we take this ray very close to the principal axis. But when we draw a diagram, so for neatness, we just draw it a little further from the pole. When an incident ray falls on a certain point, let's say it's A, and gets reflected back and passes through the center of curvature. Now what exactly happens? This would be the normal of the center. This is the reflected ray. Okay, this passes through the focus actually, not the center of curvature but the focus. This is the normal drawn. Remember I said earlier in early lectures that whenever you actually draw reflected rays, you draw a normal to the plane. This is the plane right now. This is the normal. This is the incident ray. This is the reflected ray. The incident ray strikes the surface, gets reflected back with the same angle. Okay, so this angle would be same as this angle with the same angle. Now, if we see this triangle, it is an isosceles triangle in which this part, this segment, this line segment are equal. You can see these two line segments are equal and these two theta are equal. How these thetas are equal? How would we determine how much angle is it? We can determine by the law that whenever a line intersects two parallel lines, whenever this normal line intersects two parallel lines, what are the parallel lines? This incident ray and the principal axis. Whenever this intersects the incident ray and the principal axis, what would happen? This angle would be equal to this angle. This outward, this you can say external angle would be equal to the internal angle of this triangle. Okay, so here we know that this angle would be equal to this angle and this angle would also be equal to this angle. So eventually these two angles would be the same, would be equal to each other. Okay, so now if this line is equal to this one, what would we actually determine from it? If what would actually tell us about the spherical mirrors, we would get to know that the focal length, this is called the focal length. The focal length, the distance from the focus to the pole is called the focal length. Okay, the focal length is equal to half of distance between center of curvature and the pole. Remember that the distance between center of curvature and the pole is known as the radius, or we can say r. So half of it is known as the principal focus, from which the reflected ray actually passes. And the reflected ray actually cuts off the principal axis. So this is what we wish to determine when we talk about focal length and focal point of concave mirror. So this is the focal point, this is the focal length. This focal length would be equal to half of distance from the center of curvature and the pole. Mathematically we can write as the f equals to 1 by 2r. Sometimes we denote it by capital F and sometimes by small f, but here we have determined it by small f, so we will write f equals to 1 by 2 r. Okay, so this is how we can determine focal length. This is for the case of concave mirror. Now coming to the case of convex mirror. Okay, what would happen for convex mirror? This would be a little tricky question. Okay, so in convex mirror we see that this is the incident ray, this is the reflected ray, and the reflected ray does not actually pass through any center of curvature because the center of, you can see this is the sphere, so center would be somewhere in between it. Okay, so this is the sphere, this is the center of curvature. So how would we calculate the angle and the distance covered by this ray and all that using some kind of center which lies inside the sphere, which is not in the plane of reflection of the ray? How would we calculate it? We will just draw the reflected ray again inside the circle. Let's suppose this is the incident ray, this is the reflected ray. Okay, now what would happen? We will just, you can say, draw this line. It will continue to travel this way until we just reach the focus point. Okay, you would remember that in this case the initial ray was parallel to the principal axis, and after during reflection it passed through the focus. Here the incident ray is parallel to the principal axis, and after reflection it passed through the focus. Exact same case. So what we have to do, we just have to redraw this this line segment till we reach the focus point. Okay, so this will be our actual diagram. Now we have to draw the normal to this surface, so we will draw normal to the surface and we'll get to know that these two angles will be equal to each other. So this will be the normal to the axis. When we redraw this normal back to the center of curvature, we will again get an isosceles triangle where this line segment will be equal to this line segment and this angle would be equal to this angle. So it's just simple as that. So from this figure, what we would be able to determine? We would be able to determine again that this focal point is as away from the pole as it is away from the center of curvature, which means that this distance from the focal point to the pole would be equal to the distance of pole to the half of the distance of pole from the center of curvature. So that's why it's called the focal length, the length of focus from the pole, which is half of the distance between pole to the center of curvature, or simply the radius. So mathematically we can again write it as F equals to half of R. But remember that here we would put a negative sign. Why do we put a negative sign here? Because this image was formed behind the mirror. Okay, this is the focus point. This is where the image is meant to be formed. As this image is formed not in front of the mirror but behind the mirror, okay, virtually behind the mirror. So in this case the image will be virtual and there would be a negative sign with the focal length. So there would be just a difference of signs for the concave mirror and a convex mirror. Okay, the image formed by the concave mirror, which we studied earlier, was real image because it was formed in front of the mirror. But in this case the image will be virtual image. Okay, so this would be formed behind the mirror. Coming to our last topic, image formation and ray tracking for spherical mirrors. We have taken both the cases, the concave mirror and the convex mirror. First we will discuss the concave mirror. Now, if we want to determine how image is formed, how any point of the image is formed, let's say a point is equal to a pixel. Okay, if we just take this arrow as an image, okay, this is an arrow and we want to identify how this point of arrow is formed or where this point of arrow is formed. So what would we do? We have to know about the 4 rays which would eventually gather at this point to form the pointy part of this arrow. Okay, so what exactly are these 4 rays? These are C ray, A ray, F ray. Should write it here as F ray somewhere. F ray, and the P ray. CAFP. These are the 4 types of rays that would pass through this point. Okay, they would converge at this point. Now, what is A ray? The ray which initially travels parallel to the principal axis and after reflection passes through the focus point and meet at the point where the object actually is. This is the A ray. What is the P ray? P ray is the one which strikes the pole and gets reflected back to the point where the object actually is, making an angle in which the initial angle would be equal to the final angle, or the incident angle would be equal to the final angle. In this case, in the case of P ray, you can see the principal axis acts as the normal ray. Here, this ray strikes the surface and gets reflected back, but you can see the principal axis lies just in middle of it, making itself the normal axis to this incident and reflected ray, or we can say the P ray short. The third one is F ray. F ray is, you can say, the opposite of A ray. A ray first travels parallel to the principal axis, then gets reflected back, passing through focus. F ray first passes through focus, strikes the mirror and gets reflected back parallel to the principal axis. So A ray and F ray, these are pretty simple things. Now coming to the C ray. C ray is the light which strikes this surface and gets reflected back with 0 degrees. Okay, so it gets reflected back at the same path. So here comes the C ray, it gets reflected back in the same direction and may meet the point where the object actually is. So these four rays will eventually make up the point, this point, which would be seen in the mirror. So now if we want to see the whole arrow, how would we see it? There is the four ray combination for this point. There would be another four ray combination for this point. There would be another four ray combination for this, and for this, and for this, and for this, this, and for all of these, and eventually they will make an image. So for every point, remember that there are millions of points in it. We have just drawn about 3 or 13 or 14 points. So when we just join these points, it makes up the original image. Remember that in this case it is the real image. Why? Because this image is in front of the mirror. It's not behind the mirror. Okay, it's not behind the reflective surface. Now the last topic, the image formation and ray tracking for convex mirror. What would happen in this case? The similar rays would pass through this reflective area. First we would consider the A ray. In this case, what would happen? A ray, as in this case, A ray comes parallel to the principal axis. A ray would come parallel to the principal axis, gets reflected back, passing through the focus. Gets reflected back, but it's not passing through the focus. But what would we do in case of convex mirror? We redraw this reflected ray. We have to redraw this reflected ray here. Okay, so when we withdraw the reflected ray, we will see it again passes through the focus. Similarly, the P ray strikes the pole, gets reflected back to the object point. This P ray strikes the pole, gets reflected back. Actually, this is not the back in image formation. This is the back. Gets reflected back, passing through the object point. Okay, this is the P ray. Here again, in this case, the principal axis would act as a normal to the surface. So the angle of incidence would be equal to the angle of reflection. Coming to the third ray, which is F ray. F ray is pretty simple. This ray would come to the path of the focus. You can say it's coming to the path of the focus point here and gets reflected back parallel to the principal axis. This line is parallel to principal axis. Okay, just as we seen in this case, this ray passes through the focus and gets reflected back parallel to the axis. This ray passes through the focus, gets reflected back parallel to the principal axis. Last one is the C ray. I have drawn this C ray a little more, you can say, more thick kind of ray, because it was not, otherwise it would not be easy to just to differentiate this ray from the other ones. Okay, this ray, as I've told you, would strike the surface and get reflected back on the same path. It would not make any angle at all. So the reflected ray would be in this direction but can be redrawn back to the plane in this direction. Why is it called the C ray? It is called the C ray because after reflection it passes through the center. Just in this case, after reflection it was passing through the center. This is the center. In this case also, when we would redraw this line, it would pass through the center. but these all four lines would meet at a point, and this is the point where the image would be formed. So in this case, the image would be virtual because it would be formed behind the mirror, and in this case the image would be real and it would be formed just in front of the mirror. Okay, so this was all about the spherical mirrors and how where the focus and the focal length lie. Thank you so much, everyone.